Hello and welcome back to Math 360. Today we are carrying on looking at infectious disease models. Specifically, we're going to be looking at an extension to the SIR model, which we met previously. And now we're going to include something called demography. In other words, we're going to be including births and deaths for our host population. So by the end of today, you should understand what I mean by demography and how we can incorporate this in a simple SIR model in continuous time. So in the last couple of lectures, we've been talking about infectious disease models, and those models have essentially been treating the dynamics as being occurring over a very short period of time. That's because in our equation for our susceptible class, for example, DSDT, we had a term something like minus beta Si. And so there was just loss of susceptibles from the population. So once this pool of susceptibles gets depleted to a certain level, there's not enough individuals that are susceptible to sustain an epidemic. So the epidemic will eventually die out. So that's pretty good over a short period of time. However, over a longer period of time, we want to factor in host demography. So in other words, changes in the host population size due to births and deaths. So we're going to be thinking about how this pool of susceptible hosts actually becomes replenished due to this turnover in the population. Okay, so let's start off with a transfer diagram and think what this might look like. So suppose we've got our SIR model just like we had before, which looks something like this. We've had infections, which takes you from the susceptible state to the infected, and in this case, infectious state as well. And then we had recovery followed by permanent immunity. So note there was no disease-associated death in this model. Now to have host demography, we're going to add in births, and we're going to assume that everyone who is born in this population, the newborn individuals, they're all going to be susceptible. And then we're going to assume loss from each of these classes. So these red arrows are all going to be deaths. So we're going to have births coming into our S class and then deaths coming out of our S, I, and R classes. Okay, let's start off by writing down our SIR model. And I'm going to start by, first of all, writing down the model that we had without demography. So our DSDT equation was just minus beta Si. Our DI-DT equation was beta Si minus gamma I. And our dr/dt equation was equal to gamma I. Now I'm going to assume, first of all, that we have a per capita birth rate B for our birth rate here. So this means that every individual in the population, there are n individuals, S plus I plus R, is going to be reproducing, and then they all go into this S class as we have on our transfer diagram. And then I'm going to assume that there is a per capita mortality rate of D, and this is going to function in each of these classes. So in each of these cases, we're going to have a minus D times by either S, I, or R. And this gives us our per capita birth rate or death rate. Now, I'm also going to make an assumption that B is equal to D. So our birth rate is approximately equal to our death rate. And the reason I'm doing this is because this allows us to fix our population size. So if you sum all of these together, you can check that dn dt is equal to 0. So we're going to assume there's no disease-related deaths, but our births basically counteract our deaths and our population size isn't changing. So that just keeps things relatively simple. So let's start off by finding our basic reproduction number. And remember, this is going to be our growth rate of our infectious class. When rare, I'm going to look at its per capita growth rate. So what is 1 over I times bi di dt? Well, this is beta S minus B minus gamma. The reason we've gone to minus B here is because all of these now, these D's, are just going to be replaced with B's. So we're going to have B plus gamma. And here we're going to have B plus B times by R. So we've eliminated our d's from this equation because we've assumed that b is equal to d. So to get our per capita growth rate of infected individuals to grow, this needs to be positive. So with a little bit of rearranging, we see that we need beta s over b plus gamma to be greater than 1. So remember, we're dealing with our basic reproduction number. So this is when s is equal to n or approximately equal to n. We require our R0 to be equal to beta n over b plus gamma, and this has to be greater than 1 for an epidemic. Okay, so this is pretty similar to what we saw previously in our SIR models, where we just lacked this term in the models that didn't have any demography. So let's think a little bit about scale and think about something like humans, where we have a life expectancy of around 80 years. In other words, our 1 over b is going to be approximately equal to 80 years. And take something like influenza, which has an infectious period of around a week. So in other words, 1 over gamma is going to be approximately equal to 1 week. So it's pretty clear that our birth and death rates are going to have to be a lot less than our recovery rates. So what does this mean for our R0? For our R0 is going to be equal to beta n over b plus gamma. And so the b in this denominator is going to have very little effect. It's going to be very, very small relative to gamma. And so beta n is approximately, R0 is approximately to beta n over gamma. In other words, the demography has very little effect on R0 in something like human populations for infectious diseases like influenza, which are occur over a very short period of time. So it has a very little effect on R0, but does have a big effect on long-term dynamics, which we'll get to in a moment. This simplification is one of the reasons why we will often, in a human epidemic, we will ignore demography if it's a relatively short period of time, occurring over, say, days or weeks. Then we don't really care quite so much about births and deaths that occur from other causes. Okay. This does matter, though, in the long term, and also for many infectious diseases where the lifespan is much shorter or the infectious period is much longer. So this could be something like HIV in humans. It could be animal diseases or plant diseases where their lifespans may be perhaps a lot shorter. So let's start by analyzing this model, and we're going to rescale it, first of all, by setting our population classes to be proportions rather than densities. So we're going to have U as our proportion susceptible, V as our proportion infected, and W as the proportion recovered. Then we're going to rescale time according to this sum that was found in the denominator of our basic reproduction number, recovery rate, and our birth, or in this case, it's actually the death rate, but we set the death rate equal to the birth rate. So we're going to do this rescaling here. You can have a go at practicing this if you want to pause the video, and then I'll run through it in a moment. Okay, so let's rescale our U class, our susceptible class, first of all. This is going to be the product of ds dt times by du ds times by d uppercase t by d lowercase t. So this is bn minus beta si minus bs, all multiplied by 1 over n times by gamma plus b. So the 1 over n comes from our du ds, and the 1 over gamma plus b comes from our dt dt. This then gives us b over gamma plus b minus beta. Well, we've got an s and an I here. Remember, s is just un, and I is equal to vn. So we would have a squared term here for our n and a u and a v in our numerator. And we're dividing this by n times by gamma plus b. So those n's are going to cancel. And then at the end, we've got a minus b, bu. And then we had an n here, and the n is going to cancel with the n in the denominator, and we'll divide it by gamma plus b. So we can see that these two terms here are pretty similar. So we can write this as b over gamma plus b times by 1 minus u. And I'm going to rewrite this term here as epsilon. So the previous slide asked what is epsilon. This epsilon here is going to be the ratio of our death rate to our overall loss from our infected class. So individuals are removed from our infected class at a rate gamma plus b. This gives us our birth rate b, which is also equal to our death rate here. It's the ratio of that demographic rate to the total loss from our infectious class. And as we discussed in the previous slide, b and d, because they're the same thing, are going to be very, very small relative to gamma. So this is going to be pretty close to 0. So that's why it's an epsilon here. Okay, so we still have this second term in the model. So we're going to have minus beta n uv over gamma plus b. I'm going to rewrite that based on our R0 from the previous slide. So note that this beta n over gamma plus b is just our R0 that we had previously. So we'll end up with R0 times by uv. That's our rescaled equation for du dt. For dv dt, we go through the same process. Now we're going to have beta si minus b plus gamma all times by I, multiplied by the same factor 1 over n times by gamma plus b. We're now going to have, again, a beta n uv over gamma plus b minus a v term at the end. So note here, this second term here, we would have had minus b plus gamma times by vn. We'd be dividing this by n times by gamma plus b. So these terms cancel, and that's why we just end up with a minus v there. So both of these terms here have a v in them, so we can take out a common factor of v. And again, this beta n over gamma plus b is R0. So we're going to have R0 times by u minus 1, and all of that multiplied by v. Okay, finally, our equation for the recovered class is going to be gamma I minus b r, all multiplied by 1 over n times by gamma plus b. Multiplying this out and doing the substitutions for I and r, so I is equal to Vn and b is equal to Wn. We're going to get gamma v over gamma plus b minus bw over gamma plus b. So what do we have here? Well, note that we have this first term here is v times by 1 minus epsilon. So we defined our epsilon up here. If we do 1 minus epsilon, that's going to be 1 minus b over gamma plus b, which is going to be gamma plus b minus b over gamma plus b, which is just gamma over gamma plus b. So that gives us this term here, or this factor here, as being 1 minus epsilon. So we're going to have 1 minus epsilon times by v minus epsilon times by w. So again, we have this term, this factor here as being epsilon. So we have these three equations. Epsilon times by 1 minus u minus r0 uv, r0 u minus 1 times by v, and 1 minus epsilon times by v minus epsilon times by w. These are the equations given above. Okay, because we've got a constant population size here, we don't really have 3 degrees of freedom here. We've just got 2 given by any 2 of these equations. So if you know any 2 of these values, either u and v or u and w or v and w, you can work out the third one because u plus v plus w is equal to 1. So that means that we are not really solving this in 3 dimensions. We're solving this in a triangle on the UV plane. So we can eliminate W. We could eliminate any one of these if we want to, but we are, for argument's sake, just going to eliminate W. And so this is the triangle that we are operating on. We've done this previously where we sketched out in the UV plane. So this is U and this is V. The region which we can operate in is given here by this triangle. And this line here is the line U plus V is equal to 1. So we can't have our proportions being greater than 1, and we have to operate within this triangle. Okay, so there are two equilibria in this model. One is a disease-free equilibrium, and this occurs at U is equal to 1, V is equal to 0. This should be pretty obvious. If there's no infection around, then nothing's going to happen in terms of our epidemiology. There's also an endemic equilibrium, which I refer to as EE. This is occurring when both our susceptible and infected populations are present in the population, so that neither of these are equal to 0. So in other words, we need to find U star V star being non-zero. So what happens when dV dt is equal to 0? That implies that R naught U star minus 1 must equal 0. Or in other words, U star must equal 1 over R naught. And at the same time, we need du dt being equal to 0. So that implies that epsilon times by 1 minus u. Now, 1 minus u is just going to be 1 minus 1 over R naught. Note that the reason that we assumed that V star was non-zero, which gave us this condition here. So we can't have V star is equal to 0, just to make sure that's clear. So we substitute in our non-zero value of U star. So we end up with epsilon times by 1 minus 1 over R naught. The same reasoning here that we can't have U equal to 0. And we're going to have minus R naught times by V star. And we're going to multiply this by U star, and U star was just 1 over R naught. So these R naughts here are going to cancel. This must be equal to 0 because we're at an equilibrium. So we can rearrange this and we get V star is equal to epsilon times by 1 minus 1 over R naught. So these two equations here give us our non-trivial equilibrium. Note that these don't sum to 1. There's also our value of W, our proportion of the population that is recovered. So we can work this out just by looking at simply U plus V plus W must equal 1. So our endemic equilibrium is therefore U star is 1 over R naught, V star is epsilon times by 1 minus 1 over R naught. And note that this is only realistic when R naught is greater than 1. So this is only positive when R naught is greater than 1. In other words, we don't have an endemic equilibrium if we can't first have an epidemic or infectious disease spreads. If it can't spread when rare, then it's not going to be able to be maintained in the population. Okay, so that's our endemic equilibrium. Let's think about our stability now. So let's first of all calculate our Jacobian for our U and V. So here we're going to have minus epsilon times by, minus epsilon minus R naught times by V, minus R naught U, R naught V, and R naught U minus 1. We've done quite a lot of finding Jacobians recently, so I'm not going to go through that in detail. But as you know, we need to look at our eigenvalues or just use the Routh-Hurwitz criteria at our endemic equilibrium. So if we substitute in the values that we found from the previous slide, our V is going to be equal to, let's see, we have epsilon times by 1 minus 1 over R naught. If you substitute this in to the equation here, you're going to end up with minus epsilon R naught, minus 1, and epsilon R naught minus 1, and 0. So we could find our eigenvalues, but I'm going to use the Routh-Hurwitz criteria. So let's consider our trace, which I'll call tau. Trace of our Jacobian is going to be minus epsilon R naught, which is always going to be less than 0. This is always negative because epsilon and r naught are positive parameters. And our determinant, which I'll call delta, is going to be equal to epsilon times by r naught minus 1, which is greater than 0 if and only if r naught is greater than 1. In other words, our endemic equilibrium is stable when it exists. So we know it's stable whenever it's biologically realistic. We don't know whether it's we approach it in a oscillatory manner through a stable spiral, or if we approach it monotonically if it's a stable node. So let's consider our discriminant. So our trace squared minus 4 times the determinant is going to be equal to epsilon squared r naught squared minus 4 epsilon times by r naught minus 1. Now, one thing we can note here is that when epsilon is relatively small, which we're going to be assuming for things like human infections, at least for many, say, respiratory illnesses like influenza or COVID, this epsilon here is squared, and epsilon is going to be relatively small. So this is going to be approximately equal to minus 4 epsilon r naught minus 1 if epsilon is small. So what does that mean? Well, epsilon is positive. We've already established that r naught is greater than 1. So this is the minus the sum, the product of two positive numbers. So we end up with something that is negative. So this is going to be negative if epsilon is sufficiently small. In other words, our endemic equilibrium is a stable spiral as long as our demographic turnover is relatively slow. Okay, so what are the implications for the host population then if the endemic equilibrium is a stable spiral? So let's think about what this looks like, first of all, if we were to sketch something in the UV plane. Well, we've got some value, U star, B star, and suppose we start off with a lot of the population susceptible and not many infected. Well, this point here is oscillatory stable, so we're initially going to have a boom in our epidemic, and then we're going to have a depletion of susceptibles. So our epidemic is going to crash. And then this is going to allow our infected individuals to recover. Once we reach a certain threshold, we're going to have an epidemic. And so we're going to be cycling in. So we know this is a stable spiral, and we're going to be approaching something like this. So we have a trajectory that looks like that. If you were to plot this as a time series, so suppose now instead we plot, say, just our infected population V. What would this look like over time? Well, we'd have our initial epidemic wave, and then we have a depletion of susceptibles. We don't crash to 0, though. We fall to some lower level before having a second wave, and again falling to a lower level, third wave, and so on. And so these oscillations get smaller. We can see that the oscillations get smaller because in this graph over here on the left-hand side, none of our trajectories cross each other. So if we think about this outer trajectory here, we reach a higher level of V than we do when we come back around the second time or the third time or the fourth time and so on. So each of these waves is getting smaller in size. So you can think of this as of the successive waves of our epidemic. So this is wave 1, this is wave 2, wave 3, and so on. And eventually these are decaying in size. So eventually we'll settle down at this endemic equilibrium, but we'll approach it through multiple epidemic waves, each of them getting smaller in size. Okay, that's the end of this lecture. There are a couple of self-study problems here to practice finding the stability of our disease-free equilibrium. And for students at SFU, you can access the Jupyter notebook on Canvas and explore some of these dynamics numerically as well. Okay, thanks very much. I'll see you at the next lecture.